We now talk about self-inductance of a coil. So suppose you just have a single coil, and in this single coil the current is varying with time. So you have a time varying current. So then the coil will experience a change in flux. So as the current will vary, the flux will vary. So now because of Lenz's law, this will produce EMF in the same coil. So notice we have same coil here. So the coil has a time varying current. The current varies, which varies the flux, and because of Lenz's law, there is an EMF produced in the same coil. And that is precisely why this is called self-inductance. Now this phenomenon is called self-inductance. So again, the flux changes coil by coil. So N times the flux is proportional to, so this is directly proportional to sine, the current produced. So again, the L is the proportionality constant and it is called self-inductance. And then you rearrange it, you get this flux phi is equal to L times I over N. So L is called self-inductance. Now you use the formula, you know the EMF is given as this is equal to minus N d phi by dt. So you can see that d phi by dt is equal to L by N di by dt. L is a constant because it is a proportionality constant. N is the number of turns in the coil, that is a constant, and then you have di by dt. So when you put it in here, N cancels out with this N, so this N cancels out, and you get E as minus L di by dt. So this is the EMF produced because of self-induction. We now talk about self-induction in a solenoid. So in the previous chapters we derived the magnetic field for an ideal solenoid. So the solenoid had length L, the number of turns were N, and the cross-section area was A. So the magnetic field we had derived before was this. So this is what we had derived in the previous lecture. So the flux is given as, you know, is the integral of B vector dot dA vector, and this becomes B dA cos theta. Now this theta is 0 for an ideal solenoid. So that is the cross section area of the solenoid. The solenoid looks something like this, and this was the cross section area of the solenoid. So this cross section area, this is perpendicular to the flux. So this is perpendicular to the flux, but we are always talking about the vector normal to the area. So the area vector has an angle 0. So if the area is like this, this yellow is the area vector which is normal to the area. So theta is 0 between this yellow line and the green lines which represent the field. So this just becomes 1. So this becomes equal to, this expression now becomes equal to integral of B dA. B is a constant, this becomes B times A. So this is how you get flux as B times A. You plug in the value of B right here. So you plug in the value of B times A, and L you copy down from here. L is equal to N phi B divided by I. So this is what it is. So you plug in the value of B here and you get the formula for self-inductance of a solenoid. So A is the cross-section area. So again, recap that. If the area is given like this, the normal vector of the area is like this, and that is precisely what we use in the computation here. The magnitude of this area vector is always equal to the area A here. So now we just compute an example where we just plug in some numbers. So say if the number of turns is 200, so N is 200, that is capital N. The length is 40, this is L, and cross section area is 4 centimeters square. This is A. So you plug into the formula right here. Mu naught is 4 pi into 10 to the power minus 7. We put in the area, N square divided by the length. So you get approximately 5 into 10 to the power of minus 5 Henry. Now, if the current decreases at a constant rate of 100 amperes per second, then the self-induced EMF, so EL is given as minus L di by dt. So you see there is no negative sign here because the current is decreasing at a constant rate. So we would have put a minus 100 here, and then you had minus 5 here. So minus minus sign cancels out. So this becomes 5 into 10 to the power of minus 3 volts is the answer for the EMF induced by the self-inductance of the coil.